Hello, everyone. Welcome to this session. I am Cedric Vidal, Principal AI Advocate at Microsoft, and we are going to be talking about practicalities of fine-tuning Llama 2 with AI Studio and Llama 370B today. And I have the pleasure to be here today with Shishir and Bala. Can you guys please present yourselves?
Yeah, hello folks. My name is Shishir G Patil, and I'm a PhD student with the Berkeley AI Research and the Sky Computing Labs at UC Berkeley. I'm super excited to share some of the research that we have been doing today along with Cedric and Bala. On to you, Bala.
Thanks. Hi, folks. My name is Bala Venkataraman. I'm a PM in the Azure AI team, and I work on RAG and fine-tuning on our LLMs, and very happy to be here. Let's get started.
Yeah. So, large language models. So I believe with ChatGPT and all the other large language models out there, you know very well the subjects. But just to get an idea of who is in the audience today, who has done in-context learning or prompt engineering before? Raise your hand. OK, everyone. That's to be expected. Who has done RAG? Oh, wow. That's a lot. Now, you two, I know. Who has done fine-tuning? OK. Who has done fine-tuning successfully? Yeah, you, I know. No, I don't see any hands, I think. Not a single one. No? Yeah? No, not a single one. OK. That's what I thought. So now today, we're going to try to demystify this. Yeah, large language models are very good at generating information that looks very convincing, but for most domain applications that you might have, you don't want to be generating something that looks true. You want to generate truthful, factual, useful information. And that's a key differentiating point for your domain application. How do you go about that? It's called grounding, and there are multiple techniques to do that. In-context learning is one of them. But the problem of in-context learning is that you are limited by the length of the context, right? There is only so much that you can cram into the context. So very quick, you're going to hit those limitations. Another technique is RAG. RAG stands for Retrieval Augmented Generation. And the principle is that instead of cramming everything into the context, which is very small, we are outsourcing. We are indexing all the domain documents into a vector database or a database, because a lot of databases nowadays are adding vector similarity search functionalities. And you bring a subset of those documents relevant into the context, just a small subset, and generate using that subset as the context, which allows you potentially to query and to have the LLM work with a very big domain, as big as you want. But the subset of information is still going to be limited by the size of the context. And also, one of the other limitations is that sometimes you're going to get into the context documents that you don't care about, that are not useful to generate a useful answer. So that is called bad precision, sorry. And bad recall is when you're going to be missing out on documents that would be useful to bring into the context are not going to be, and therefore the quality of the answer is going to be subpar, and that can be problematic. Depending on your domain application, it can be more or less, and sometimes it can be so problematic that it's completely useless. It's possible for some domains. So what do we do about that? No, sorry, how is RAG functioning? I was forgetting that I had that slide. My apologies. The principle of RAG is that, as I was saying, we index the documents into a database. And for each document, we're going to split them in chunks, small chunks, for which we're going to create vectors. And when the user is going to ask a question, we're going to create a vector for that question search the database for all the chunks which are close in the vector embedding space from the query's vector using semantic similarity search functions such as cosine similarity. We're going to take the top k results, bring them into the context, cram them into the context, I should say, and then generate the response. So here's what it looks like. And like I was saying, there are some limitations, and fine-tuning is one of the ways that we can improve some of those aspects. Bala?
Thank you. So like Cedric alluded to, RAG comes with its own challenges, right? I mean, while it's very effective to easily get, in context learning and a bunch of stuff, it has its limitations. Even with RAG, there is only so much in terms of context you can send to your model. I mean, context length has its limits. And the more context you send, you have latency issues. It's going to be slower, and the more context you send, it's going to be costlier as well because of token charges. So what do we do about that then? We go to fine-tuning. To get started, what is fine-tuning? Fine-tuning is like taking an off-the-shelf model and training it with your own custom data to do a specific task. Let's take the example of a postgrad, right? Let's say you did undergrad in medicine and you're ready to become a doctor, but now you want to do postgrad and become a brain surgeon. So you fine-tune yourself on top of what you've already learned to do a specific task, which is brain surgery. Fine-tuning is very similar to that. You take a great LLM, train it on your data, and make it a great LLM for your task. That's what we're trying to do with fine-tuning. So what are the benefits of doing something like fine-tuning, right? First one is, of course, better performance. We'll see later in our key takeaways how we've improved the performance. But to get started, you have trained this data on your you have trained this model on your data for your specific use case, so it's definitely going to perform faster and better than an off-the-shelf model, number one. Number two is it's cheaper. You don't need to use a large, expensive model, which is good at a lot of things. You can take a much smaller, cheaper model, train it to do a specific task which you want. So you spend lesser, much lesser in terms of money. We will see this also in our takeaways with an example. And lastly, differentiation, right? You're not taking any generic model and making it do something. You've trained your model to do something really good. It might be one task, but it's really good at doing that task. So you're able to differentiate yourself in the market in terms of your model, how well your model behaves. So is everything hunky-dory with fine-tuning? No. We saw that when we asked people to raise hands, how many of you have done fine-tuning? Very few raised their hands, and when asked how many of you did it successfully, hardly anyone raised their hands. There are some reasons for that. First one is data. I talked so many times about data when I talked about fine-tuning. So it means you need good quality data for fine-tuning, and you need lots of good quality data. Very less good quality data is not good enough, and bad quality data is actually detrimental to to a model. You might actually make it worse than it was before. So good quality data, how do I come across and create good quality data? Number one. Number two is to run training on these large models, you need a lot of computational horsepower, a lot of GPUs. Not everyone might have the budget to procure something like that and maintain it, right? That's another thing. Let's say you got data and computational horsepower. Does your organization have the expertise to stitch all this together and run something as complex as fine-tuning? That is another challenge. So you need data, you need computational horsepower, and you need the expertise to run all this. Now, how do we get across all this? The rest of our talk is going to deal with each of these and see how we can make your life a little simpler. And by following what we're saying, we'll also go show you what results we saw. All right. Cedric.
Okay. Thank you very much. So, as a recap, we saw in-context featured learning, and we saw how it's super easy. Most of you have done it successfully, and it's very useful for a lot of applications, but there are some limitations. We have seen RAG and how it allows to bring a subset from a very large, potentially, amount of documents specific to your domain. And then we've seen fine-tuning, which allows you to build smaller, faster, more efficient, but still can hallucinate. So where do we go from there? Well, it happens that UC Berkeley's Skylab has published a paper recently called RAFT. And Shishir here, one of the authors of the paper, is here today to talk to us, explain to us how it works. Stage is yours.
Thank you. Folks, buckle up. No, I'm just kidding. So my goal for the next 10 minutes is to make you all experts in RAFT, okay? And I'm going to try to do that so that everyone at the end of it understands what's going on. It's not going to be hard, trust me. So let's get started. In short, RAFT stands for Retrieval Augmented Fine-Tuning. Okay, so you're going to fine-tune an LLM to make it aware and good at RAG, right? So can you fine-tune an LLM for RAG, in short? Now, to understand the RAFT concept, let's take a very simple analogy, right? So I'm a PhD student, and one thing that I do a lot is take exams. One way to prepare for the exam is to study for the exam. So I know which subject it is, I take the textbook, and I understand the concept, I memorize some of the ideas, and that's one way to prepare for the exam, right? And so this, in LLM parlance, is fine-tuning. It's when you train the LLM to be relevant, to be well-versed in a particular concept, that's preparing for the exam, and that's a closed book exam. Another kind of exam is open book exams. So I go into the test, taking all the textbooks I have, and then given any question, I can refer the textbook to answer the question. But here's the deal, right? I'm a PhD student in computer science. If you take me to an exam in the legal school or in the medical school, and give me all the textbooks there is, I'm not going to be able to do much well, because I have no idea what the textbook does. So in LLM parlance, this is RAG. If you train your LLM for one context or a general purpose context, and no matter how good of a retriever that you use, if you were to use RAG and shove a bunch of context to your LLM is going to have no idea, right, what document does what, much like how I'll have no idea which textbook does what. So with RAFT, our idea was, can we actually prepare for the exam lightly, right? So if I know that I'm going to go to an exam in the law school, and I get all the textbooks ahead of time, then I can quickly index the textbooks and the chapters. So given a question, I know exactly which textbook and which chapter to refer to answer the question. I can do much better, right? So in LLM parlance, this is RAFT, a technique to fine-tune the LLM to do better at RAG, right? And so how do we do RAFT? It's simple. So there's two parts to this. I'm going to tell you what the training procedure is, and then I'm going to tell you what the inference procedure looks like. In the training procedure, one of the key ideas here is, can you make the LLM discern and discard distracted documents, right? So for the question, who invented the transformers, the relevant textbook, or the document in this case, is Attention Is All You Need paper. But at train time, I'm also going to introduce distracted documents. So maybe 3 different papers on ResNet, a popular machine learning model, and say Adam optimization technique, and GLOW as well. So when I introduce these distracted documents at train time, I'm training the LLM to discard distracted documents and pick the right documents, right? Now, why am I doing this? The idea is simple. This is how you're going to use your LLM at inference time, so why not also train the model to behave similarly at train time as well? So what's going to happen at inference time, right? So at inference time, the same thing. The user is going to ask a question. In this case, the question is, can transformers be used for images? And then your retrieval, and this could be your BM25, any off-the-shelf retriever, is going to retrieve the top K documents, right? So in this case, it's ResNet, Vision Transformers, and VGG. And what the LLM is going to do is it's going to pick the right document, discard the distractors, and then answer the question. So in this case, yes, with Vision Transformers, you can actually also feed in images as input, right? So that's the idea. Is this it? The answer is yes and no. At a high level, this is pretty much it. There's also a few interesting tricks that we do. One is how do you prepare the data set, right? So suppose there's a question, which is the Oberoi family is part of a hotel company that has a head office in which city? Now, this is a very popular question from a popular data set called 𝗦𝗲𝗀𝗀𝗀. And so your RAG setup is going to give you a bunch of documents, right? So each bracketed text, think of it as a sample document. And there's a bunch of those, right, including some restaurants in Jakarta. And the instruction is, given the question, please look at the documents and come up with an answer. So what we do at train time is also include a chain of thought style answering. So it's chain of thought plus, right? So the first thing is you're going to reason and say, look, I'm going to look at two documents. And so the begin document and the end document within hashes are verbatim citing the document. So you're forcing the LLM to cite the document that it's going to use to answer the questions. So here the LLM is going to reason and then cite the two documents that it's going to use verbatim, and then use these two documents to answer the question, which at the end you can see is Delhi. Right? So the idea is you give the LLM a question, give it a bunch of documents. Can the LLM now pick the right documents, cite them verbatim, and then pick the answer from that by reasoning through the answer? So that's RAFT, right? How well do we perform? Well, in short, with RAFT, you can take an extremely small model like Llama 7B, and Cedric's going to show you some of the benefits in terms of cost of doing this, and actually get better performance compared to even state-of-the-art models out there, open source and closed source proprietary models, right? And so PubMed is a classical medical data set. 𝗦𝗲𝗀𝗀𝗀𝗀 is like Wikipedia-style general knowledge data sets, and the remaining three are coding data sets. So across three domains, what we show here is that RAFT performs state-of-the-art. So in short, RAFT is a recipe or a training procedure for open book question answering. In other words, retrieval augmented generation. And so if you're doing RAG, you should be doing RAFT. Back to you, Cedric.
Thank you, Shishir. So I'm going to switch to my screen. Thank you. So Shishir showed to you how RAFT functions, the concept and the theory behind it. Now I'm going to show to you how to use it concretely on your own domain. And I'm going to be using for that exercise a domain constituted of bats, vampires for the movies, and a bit of surfing because I do kite surfing, so a bit of surfing, kite surfing, windsurfing, that kind of thing to throw it into the mix. And so here's what one of those documents look like. So those are Wikipedia documents. I'm going to switch to Jupyter Notebook inside VS Studio Code. And so the principle of RAFT here, I'm going to explain the steps. And here in that code, we're going to share the repository at the end of the session so they can go look at it and try it. I'm going to run all the cells all at once. And I'm going to switch to the one which is the most interesting, which is the call of the raft.py script here, which is going to be generating the data set. And as it is starting to be running here, you're going to see progress bar here. It's going to take roughly a minute. And while it runs, I'm going to switch back, thank you, Shishir, to the slides and explain how that script works. So the first, the first step is to start with the documents that are making up your domain. Here they were in PDF format. To split them in small chunks, usually a function of the context capacity of the LLM that you want to fine tune. For each of those chunks, we are going to generate a set of questions. Think of it of, hey, I have that small extract of a big document. Find all the questions that would make sense to ask about that chunk, which means that you don't have to do it manually. You delegate the task to a big LLM. In that case, we are here using Llama 3 70B instructs to fine-tune the Llama 2 7B completion model, and more on this later. So like I said, for each of the chunks, we generate a list of questions. And for each of those questions, we then, in a separate phase, generate a few things. An answer, as well as a chain of thought. So chain of thought is now a very well-known pattern in the, I'm going to say, prompt engineering space, which allows to get very good answers, and answers for which the model has gone step by step to explain how it got to that answer. And in addition to that answer and that chain of thoughts, we're going to attach the chunk from which we generated the question, the oracle chunk, as well as some distractor chunk thrown into the mix to train the model to be robust to information that is not relevant to answer the question. We take all of that, we bundle it into a data set. This is going to be our fine-tuning data set, which we are going to be splitting in a few parts. This is classical of machine learning: a training data set, a validation data set, and an evaluation data set. The training data set is the data set which is going to be used to train the model, to update the weights in the model. The validation data set is the data set that is going to be used to make sure that the training is going in the right direction, that we are actually improving the capabilities of the model to solve that problem, that task. And then we have the evaluation data set, which we are not going to be using for training at all. We are keeping it on the side, and we're going to be using it on the final fine-tuned model to make sure that the model has been trained correctly and generalizes to data that has not seen before during fine-tuning. Same. This is very classical of machine learning. So, sorry, I'm going to switch back to my environment to show you, different screen maybe. Yes. So, as we can see, the script has completed. And as you can see, there is a chunking phase. And also, by the way, here we used only one of the PDFs. So it's just one document, and I took the smallest of the PDFs that I had, just so that for the sake of this demo, it would be fast. Because don't get me wrong, the process of generating the whole data set takes some time. It takes hours and sometimes days for big domains. But in this case, it was very fast. And we have the chunking phase where we chunk we split into multiple chunks. Then the generation phase where we generate the questions and the answers. And then we are exporting, and I'm going to have to be fast on this, but we are exporting the three data sets, splitting them, and exporting them to JSON line, which is the format that Bala is going to be using right now in AI Studio to do the fine-tuning. And you're going to be seeing how easy it is. We're going to be switching to you, Bala.
Yes, thank you.
Here we go. Oh, sorry, we're switching to your laptop.
There you go. OK, thank you. So now that we have the data, let's get cracking and let's do fine-tuning, right?
Yes.
So I'm going to go to AI Studio first, ai.azure.com. And I have created a project, UC Berkeley RAFT. And out here, I'm going to go into my fine-tuning tab. And I'm going to click fine-tune model. From the list of models, I am going to choose Llama 27B because that, as you all know, is the model we are trying to fine-tune and is the topic of our talk. I click confirm, and I see this. I'm going to fine-tune it in this project so that I store the fine-tuned model in this project. And I can see the pricing and terms here, right? What this card tells me is that it costs $34.57 per hour to train this model. So this is, if I run a 3-hour training job, it's going to roughly cost me around $100 and odd, right? And after that, if I want to deploy the model, I have to pay a inferencing cost of, hosting cost of around $3 per hour. and I also pay for input and output. And when I say I, the consumers pay for the input and output tokens, and you can, you will be paying this much, and you will pass on the cost to your consumers accordingly, so that, you know, I'm not going to go into the commercials, but it's all here. This is what it costs. And what I want to bring to your attention is here you don't have to buy all that huge computational horsepower. You can just rent it as needed and use it as you go. Right. Now let's continue to fine tune. All right, it gives me this wizard. What model name do we want? Let's put the typical build 2024 name to it and click next. What do I want to do? I want to do task type of text generation. For training data, I'm going to upload files, which Cedric has given me. I'm going to upload file, and I'm going to use the train JSON-L. I open it. It is uploaded, and it is giving me a preview so that I can make sure the right file got loaded. Yes, so it has two columns. One is text, which has the context, and the other one is the ground truth, which has the answer and chain of thought. All right, so I can map these to what the fine-tuning job needs. The prompt column is the text, which is the context, and the completion column is the ground truth. I click next, and it asks me for validation data. Cedric just explained what it was. You could, if you don't want to split it beforehand, you could also split it during the training, saying, hey, automatically split my training data, but we've already done the hard work of splitting it, so we will upload the files. And I'm going to use the valid JSON-L here. And similarly, I can do mapping here as well. Text and completion. Next. All right, so far what we did was we looked at the cost, we mapped a few columns for the data. Now we have to set few parameters. The first one is batch size. Batch size is, it determines the number of training samples which are processed before you start updating your model's internal parameters. Now think of, we talked about exams before, so let's talk about reading a book, right? Let's say you're reading a book and you take notes every couple of pages, 2 or 3 pages, you start taking down notes. So which means that you're reinforcing what you learned and making a note of it in your notebook after every 2 or 3 pages. The batch size is similar to that. After every certain point in time, you go back and update your model's internal parameters. If you choose a very large batch size, which means it means that your training will go faster, but you will update your model's parameters much lesser. If you take a very small batch size, your training is going to take much larger. It might not be cost effective and things like that. So a good balance is needed. In Azure AI Studio, what we do is we already choose the batch size for you based on what type of GPUs we will run it on. All you need to do is choose the batch size multiplier of 1, 2, or 4. More often than not, a batch size multiplier of 1 is good enough, and that's what we'll choose for this run. The next one is the learning rate. Learning rate, as the name suggests, is the speed at which the model updates its weights, right? Let's take the book analogy again. An average human being is able to read around 1 page per minute. So to read a 200-page book, you will need around 3 hours. If you read a lot faster than that, you will finish the book faster, but you may miss some of the plots or the intricacies of the book. If you read very slow, you might understand everything, but probably you're killing all the joy out of reading that book, right? So same way, learning rate also, it's important to choose the right learning rate. We have a insight slide which actually tells us how we learned from our learning rates through our experiments. But here to summarize, a very high learning rate will mean your training gets done faster again, but your model might overshoot. A very low learning rate might mean that your training takes forever to complete. Also, very low learning rates have the risk of you muting some of the properties of your base model itself. So it's good to choose the right one. For this experiment, we are going to use 0.0000002 as the learning rate. Finally is the epochs. Epochs is the number of times your training goes through the entire data set. Coming back to the books again, we all love books in exams. If you read the entire book once, it is one epoch. But sometimes maybe the book is very complex and you didn't understand everything in the first run, you want to read it again. So sometimes going through the same data more than once helps, but after a certain point, it's not, the ROI is less. So epochs also depends on the complexity of your data. For our data set, we're going to choose an epoch of 1. More often than not, we've seen that batch size multipliers of 1 and epochs of 1 are good enough. You can always run the training multiple times to see the output metrics and tweak them accordingly. Now that we've chosen all these parameters, we click next and we are ready to submit the job. So that's all we've done. Loaded the data, mapped it to required columns, set 3 parameters, and we are ready to submit. All right, it's submitting the model, and the fine-tuning job has started. If you run it on the, our full database took around 2 hours to run.
Yes.
For the fine-tuning job?
1 hour and 2 hours, depending on the job.
So once this one finishes running, you will be able to deploy it from here. Your model will start showing up. What I'm going to do is I'm going to take another model which I already fine-tuned, and I'm going to deploy that fine-tuned model. I click deploy. If you see, it's pretty much the same as a base model. It shows me this, and it'll show me again the pricing. I continue to deploy, and it doesn't like the big names. Okay, and I deploy it, and it starts deploying. It'll take a few seconds. Once it finishes, it's going to show me a screen like this, which says, hey, this is the name of your deployment, this is the endpoint, and this is the key, and you can start using it. As simple as that. Right? Now, we trained the model, we deployed it. Does it really work? Let's check it out. So I've created 2 prompt flows. Right? One for my base model and one for my fine-tuned model. Let's go to the base model first. So this is a very simple prompt flow. It takes 2 inputs. The inputs are question and context. I copy paste it, and I construct a prompt based off of the question and context, and I then pass it on to the Llama 2.7b base model, and I extract the final answer. When I extract, all I'm doing is I'm just splitting it into separate strings and sending it out, right? That's all I'm doing. And in constructing the context, what am I going to do? I'm giving it a bunch of instructions. Hey, this is the question, this is the context. Please answer it using the information given in the context. And I'm giving it more instructions like provide step-by-step reasoning as to how you got to the answer. If you're quoting something, do a begin quote, end quote. At the end of your response, always give a final answer in the form of, you know.
And this is called few-shot learning.
Yes. Yes. Yes, it's called few-shot learning. Give it in the form of answer, and I do all this, and now I go in and give it the actual question and the context. I'm going to give it from here. What kind of vision do microbats have? And that's the question, and this is the context. I'm just copy pasting one of these questions and context from the eval data set which Cedric gave me. I'm going to click run. It's going to take a couple seconds. This is a development environment. Obviously, it's not going to be very fast. It's for you to iterate and see whether things are working or not. So it's running, and come on.
Also, it was taking a nap.
Yes, it's very tired.
Waking up.
We made it work like, all right. It finished, and here's the question we gave. What kind of vision do microbats have? It completed it, and the answer it's telling me is most microbats have limited visual acuity and rely on echolocation. Okay. Let's look at the explanation. To answer the question, what kind of step 1, step 2, it tried to do something and give an answer, but Is it really accurate enough? I don't think so, because I've gone through the data set, and we'll see what our fine-tuned model does for the same thing.
It doesn't give a straight answer.
Yeah, it's not succinct. So I'm going to go open the fine-tuned model flow. It's pretty much the same in terms of what it's doing. It takes the same inputs, question and context. It constructs a prompt. It sends it now to the fine-tuned model and extracts the answer. The only difference is, let's look at the prompt construction. Nothing in it. I'm just passing the question and context as it is, not giving it any instructions. Now, I'm going to ask the same question here, and what kind of vision, and same the thing, and the outputs for that is 2 words, mesopic vision, right? It gives a very nice explanation. To answer the question, we need to identify the type of vision, and it also does a quote actually from the exact document. Most microbats have mesopic vision, which means that they can only detect light in low levels. Other mammals have photopic vision, which means they which allows it for color vision, and it ends the quote there. This is the exact place I'm getting this answer from, and based off of that, my answer is mesopic vision. And that's what our fine-tuned model does for us, with no instructions. Very cool, right? All right, one answer is not going to cut it. So what does it do for the entire eval data set? Cedric is going to tell us.
Yes. Okay, so Bala showed to us how easy it is to fine-tune a model in AI Studio. It's literally a click away. And we've showed to you how the RAFT method provides with a framework, a process to go through the fine-tuning on your own domain. In our case, in our experiment, how well did it work? Well, because Bala showed to you on one specific example. Okay, that's not statistically a good way to look at it. It's interesting, but we need numbers. And AI Studio comes with an evaluation framework which allows you to run in batch evaluation metrics. And we chose 2 in our case. We chose similarity because we are distilling from a bigger model, and we want to know how well the information has been distilled in the fine-tuned model and how well it reproduces the result from the bigger model. And groundedness, because we're doing RAG, so it's very important that the answers are grounded into the context. And in the case of similarity, we are doing extremely good. And by the way, we used a data set of 18,000 data points, tuples of questions, answers, and COT. And with that amount of data, we got similarity of 4.76, which is an improvement of 1.7 times from the baseline Llama 27B chat model to compare apples to apples. And when it comes to groundedness, it's not as good. There's something where, in our experiment, that's something we could have worked more on, especially on the prompting of the larger language model to ground better the answers. But still, it's still better than the baseline model. But what's very interesting here is that the similarity, so the problem is not so much with the fine-tuned model, it's more in the process, in the way we generated the questions. But the distillation has worked very well. When it comes to cost, it's also extremely interesting because I'm not going to go into the details of the numbers because Bala already went through them, but what matters is that it's roughly 100 times cheaper to run a fine-tuned smaller model, and the similarity, as you could see, was very, very good. So it's going to give you excellent answers at a fraction of the cost. Then, how much did that experiment cost in terms of dataset generation and fine-tuning? So the dataset generation using Llama 370B with 18,000 data points consumed 10 million input tokens and 3.7 million output tokens for a total of $80. And the fine-tuning took an hour and a half at $35 per hour. So for only $50, so for like a bit more than $100, you get an awesome, very small and efficient and cost-efficient and
Awesome model.
Awesome model. Yeah, that's the word. Awesome model. I'm losing my words. So what are the key insights? The learning rate. So you remember you had 3 hyperparameters. This is very intimidating. I get you. Like when you see those numbers, you're like, what should I put? Like, and it's a very hard question. We're going to give you a rule of thumb that works for the fine-tuning method which is used by Azure AI and with the RAFT method. In our case, we fine-tune a completion model, not an instruct model. So the completion model is a model that has not been fine-tuned for instruction following. So it's less refined. So it requires a learning rate of 0.002 and a bigger data set of roughly 20K data points. If we had been fine-tuning an instruct model, we could have used a smaller learning rate, 10 times smaller, of 0.00002, and a data set of roughly 5,000 data points should have been enough. The reason why we didn't do that is because Azure AI doesn't yet allow to fine-tune an instruct model, but this is going to change very soon. Throughput and load balancing. We're generating a huge quantity of data. That's a lot of tokens. So on Azure AI right now, you have 2 ways to do it. You have MAS, Model as a Service, which gives you 70 tokens per second. Remember, I was talking about millions of tokens that we are generating. So it's able to do 70 tokens per second. On MAP, so MAP stands for Model as a Platform. You provision your own infrastructure, and the smallest SKU that you can use on Azure is basically a VM which has 4 NVIDIA GPUs A100, which gives you roughly 140 tokens per second per VM. So if you want to go faster, you can go for that. But it's more committing because you need to manage commission and decommission the infrastructure yourself, which you don't need to do with MAS. Then you can go one step further, which we did because you know what demos are, you know what preparing a talk for a conference is. You're in a hurry. And so, well, we provisioned quite a few GPUs. We provisioned 2 MAP clusters, as well as a MAS endpoint, and we load balanced the load on all those endpoints using an awesome little framework called Light LLM, and which gave us 350 tokens per second. Upcoming, as I was saying, so you're soon going to be able to deploy, to do fine-tuning on serverless of Llama 3 instruct models, which is going to make it cheaper, easier, and allow you to use smaller data sets. And then you're going to be able to do code first to automate and industrialize everything that we showed today using the Python SDK. This is upcoming. Microsoft loves Gorilla LLM. So thank you, everyone. Here's a QR code to the GitHub repository of the code that we used to prepare this talk. Disclaimer, right now, the code is a mess. We are going to clean it. And right now, it points to a branch in my personal repository. And as soon as we merge it back into the project, the main project, it should be cleaner and easier for you to use. Right now, it's not going to be the easiest for you to use. I apologize for that.
We just completed it 30 minutes ago.
No, you're exaggerating.
Yeah.
We don't.
So here's a few talks I recommend to watch online because they were before. Thank you very much, and we have a few seconds for questions.
No.
Yes, one question.
If we train the model from data
So do you want to use the mic?
Oh, thank you.
If we have given some documents with model during the fine-tuning that we don't want to give later stage, we realized how to untrain it or how to go the back stage.
Yeah, so that's a pretty good question. And this refers to the concept of untraining. There's been a lot of research going on in this, but there's no mature solution as yet. But that's not to say that you cannot do it. Because if you delete a few documents that you don't want the model to answer, you can always discount that from your instruction data set and fine-tune another model, all right? And in terms of cost, you're not losing very much because the data set generation is already done. So at $35 an hour, you're going to be spending a few dollars. So I would say that's the best way to go today, where you get some sort of guarantees until research catches up.
Yeah, and also Azure AI uses a fine-tuning method called 𝗲𝗲𝗸𝗲, which trains only the top layer of the model, which is very cost and time efficient. So yeah, it's just much easier to go from scratch again. Yeah.
Yeah.
So I'm sorry we don't have enough time for more questions. So
But
thank you.
We're going to be here, so
Yeah.
you can just come over to us and talk, but we're going to be kicked out of stage soon.
Thank you very much.